Hey everyone, welcome back. This is week 16. I can't believe we're already week 16, but we're still working through Boyd. So this week I finished sections 4.3 and 4.4, which really cover the three sort of workhorses of convex optimization. So we have the linear programs, quadratic programs, and second order cone programs. So last week, or I guess 2 weeks ago, we set up the general theory of convex optimization problems. But now we're getting to the specific families. So I thought this week was pretty cool. Oh, then, change your scenery again because I'm back in Japan. Also, this is the same reason I didn't do any video last week. So a linear programming, or what's called LP, is just a convex optimization problem where everything is affine. So in other words, the objective function here and all the constraints here are all affine functions. So you have some vector, c multiplied by your variables of interest, x, and you want to minimize this objective function. But it's subject to constraints, and the optimal value is sort of x star, which minimizes this objective function. So notice that d is often, well, it is redundant because the optimal values of x will be the same regardless of what d is. It's just a constant. So usually people just drop it. And you can also maximize an affine objective. You just flip the sign and it's still convex. I remember learning about the geometry of the LP in my linear programming class, and I thinking it was really cool. So here's really the geometry. So we have a polyhedron. This is lightly shaded blue in two-dimensional space. So there's, the vector is 2 dimensions. We have sort of the dashed line, which is sort of the level set of the objective vector. C is a vector, right? So we want to minimize C transpose X. And so you want to go in the direction of negative C as much as possible alongside the feasible region. So the feasible region is the possible values of X, which satisfy the constraints here. So you want to find a point in this feasible region which minimizes the objective function. So sort of go in this direction the most. And you can see that this point x star definitely does that because this level set curve here, or in this case a line, is just touching the polyhedron here. So in summary, what you're really asking when you solve a linear programming problem is how far can I push these sort of level set hyperplanes in the direction of negative c while still touching the feasible set. I won't show it here, but you can actually prove that the optimum x star will always be a vertex on this polyhedron. Okay, so here's an example that I really liked. So say you want to minimize a piecewise, a linear convex function. So something like the max of a bunch of affine functions as follows. So here's what you want to minimize. You want to minimize f of x. And each of the arguments is a affine function. And you take the max of all of those affine functions here. So, this doesn't clearly look like this over here, but I'm going to try to convince you that indeed this is also a linear programming. So, the trick, which is not really a trick, is you introduce a new auxiliary variable t, and then you write it in the epigraph form as follows. So now this is just a linear programming with the objective function being very simple. It's just a variable t, and you're subject to these m constraints here. So if you look at it and stare at it for a couple minutes, you can probably convince yourself that these two optimization problems are actually entirely equivalent. So this same idea, sort of writing in the epigraph form, actually shows up, all over the place. And quote unquote trick, technically we learned it in the previous chapter, but we're just applying it to our problems. Alrighty, so the quadratic program, or QP, is a sort of next level up, so to speak. So the objective now is a sort of a convex quadratic objective function. But the constraints are exactly the same. They're still affine. And notice that P is has to be quasi-semi-definite. You can probably see how we can recover the linear programming problem from the quadratic programming problem. If we take P is equal to 0, we have the exact same problem. So linear programming is actually a special case of quadratic programming. So let's look at this diagram, and again, this polyhedron is exactly the same. We have linear constraints still, but now we have sort of these ellipsoid sort of level set curves. And what we want to do now is we want to find the boundary of P where the smallest ellipse first touches the feasible region. So in this case, that's sort of here. The gradients, negative, the gradient of x star here is sort of pointing in this direction. Now let's look at a simple quadratic programming example. So you've probably seen this before, just probably not formulated as a optimization problem. So I'm talking about the simple least squares problem. As you probably know, you have some matrix A, and you take the x and you multiply that together, you have some b that you're trying to predict. And so you just want to minimize this sort of your prediction against the actual, right? So you've probably seen this in your ML classes or statistics classes, but this is actually a quadratic optimization problem. But let's say you add some additional constraints. Say you know something about x, so x can't just take on anything. Let's say you want to constrain x to certain bounds. There's no closed form anymore. This above expression, you probably know, has a solution. X is equal to a pseudo inverse times b. So this is the analytical solution for this top optimization problem. But this problem has no analytical solution, and you have to run it through a solver, as you often have to do. Okay, I want to show you another sort of classic quadratic programming application, and I think it's actually really cool how you can easily apply it to the real world. In this case, markets, financial markets. So let's say you have n assets, and xi is how much asset of I you own. So the return is random. The price change vector p has some known p bar and covariance sigma. So for portfolio X, you can model the mean and variance as follows. So for some return, expected value return is equal to the dot product between p bar and x, and the variance, of course, is just the variance equation as follows here. Now, there's an inherent trade-off here. Usually speaking, the higher expected return is associated with higher variance, or you can say risk. So you can formulate this as an optimization problem. So let's see how we can actually do that. We want to minimize risk subject to a minimum acceptable return. So it turns out translating this problem into sort of an optimization problem is pretty intuitive. As I just said, you want to minimize the risk. So you just put the variance in the objective function, and you want to minimize it. But of course, you don't want zero return. So you want to define prior sort of some minimum return that you're satisfied with. And you're saying that the return must be above this minimum. And also sort of your x, your portfolio of stocks, must be the sum to 1, because you're just working with proportions. Is usually how they do it in finance. And all your you can't have negative assets, so they must be positive. Now, one way you can think about it is for one value of your R minimum, you get some variance associated with that. The optimal variance you can achieve with some sort of, some return that's you're expecting to be more than the minimum. Now, if you sort of sweep out different values of our minimum, what does that really look like? So what that looks like is as follows. So I plotted the variance or the risk on the x-axis and the expected mean or the expected return you would get on the y-axis. So let's say you're in the stocks and you want zero risk. You don't want to risk anything. Okay, what kind of return should you expect? Well, you go here and you realize that if you want zero risk, you can't get any returns. Your expected return is zero. Basically telling you it doesn't exist. You can't play the game if you don't want to take on any sort of risk. And as you sort of sweep out the minimum return that you're allowing, you have to take on more risk. And so, this should make sense, but generally speaking, the more risk you take on, the higher return you could potentially get. Okay, so this part I actually find the most interesting. The second order cone programs generally look like this. Okay, so you have in the constraints, you have a affine function of x, must lie inside a second order cone here. So you can show that the linear programmings and the quadratic constraints, quadratic programs, are both special cases of the second order cone problems. So let's look at where this sort of type of convex problem naturally arises. So first, let's think about a linear programming problem on the left here. So we said the subject to g of x is less than or equal to h. So this sort of implies that you know exactly what the constraints are. So you know what g is. But let's say you don't actually know what the constraints are. You just have some general idea and you can bound the constraints themselves to some bound. Now, how do you solve the linear programming? So just to clarify, I used G in linear programming earlier in the video, but I'm using A here as a sort of same designation. So A is also a constraint. So A is a constraint, and before we knew what it was, but now we don't know what it is. So you can think of it as sort of sampling from this ellipsoid, that gives us the real constraint. So now, instead of satisfying the constraint for maybe your best guess of AI or just some random guess of AI, you sort of want to minimize the objective function for all constraints, all possible constraints in this ellipse. So translating the English into math, you can see that the constraints just turn into the normal constraints, but for all AI that's in the ellipse. Okay, hopefully this makes sense. Now, if you remember earlier, we turned the max function into the individual, constraints. Now we're going to go the other way around. We're going to take a bunch of individual constraints and turn it into a max function, or in this case, the supremum function. So you can do that. You can see that these constraints are the exact same as this one here. Now, the reason we do this is because we can now expand and use the properties of the ellipse. Just going through some algebra with the ellipse here, we see that the final, rewritten objective function, constraints is as follows. We have some a bar times x, and we have this 2 norm here, where P is the matrix that defines our ellipse. So here's really the big idea I want to highlight. Look at in particular at this norm term here. You can see it's penalizing x for being large in the directions where the parameters are uncertain. So where the parameters are uncertain, they'll show up in your P matrix. And if x is large in that direction, then this 2 norm will be big. And that's not good because we want it to be less than bi. So in effect, it's penalizing the values of x, which are, where the parameters are uncertain. So, that is regularization you learn about in machine learning. So the geometry of uncertainty in your problem parameters produces regularization automatically. just forming it this way. So I thought this was really, really cool. Okay, so to recap, this week is really about categorizing notable types of optimization problems. So it's linear programming when everything is affine, the objective function and the constraints. It's quadratic programming when the objective is quadratic. It's second order cone programming when you have norm constraints, which show up naturally the moment you add uncertainty to your LP parameters. But the thing that really sticks with me is that these aren't just sort of discrete categories. There's a hierarchy. So every linear programming is also a quadratic programming, and every quadratic program is also a quadratic constraint quadratic program, and every one of those is also a second order cone program. So you sort of move up the hierarchy and you get more and more general. So next week I'll be on 4.5, and again, sorry about no video last week, but now I'm in Japan, I'm still going strong. So thanks for watching, and I'll see you next week.